Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we will extend our discussion on the thermal properties of materials. So the thermal properties of materials are closely linked with the thermodynamics branch of physics. So we'll not go into detail, but we'll discuss the important aspects, just brush things over which are required for material science and engineering. So previously we have covered the concepts of change of state, latent heat and calorimetry. In this video, we are going to discuss about another important concept related to material science and engineering when it comes to handling gases. Okay, so we'll discuss about gas laws. Now, before we discuss gas laws, I always told you that when it comes to thermodynamics, there are certain important parameters which are very crucial when it comes to establishing a relationship or writing an equation to establish the nature of a particular material. Okay, so the three important parameters here are pressure, temperature and volume. Okay, pressure, temperature and volume. So whenever you will discuss any thermodynamic behavior of a material, or will discuss the thermal properties, these three things will always be present. It's thermal means it's not only temperature, because pressure, volume and temperature are closely linked together. They're so closely connected that if we change one parameter, the other will be affected. So like that. So here we'll discuss the interrelationship between these three important thermodynamic parameters when it comes to gases. So we will establish these relationships with the help of three important gas laws. We'll discuss them one by one. So the three important gas laws here are Boyle's law, Charles' law and Gay-Lussac's law. Okay, so first we'll discuss Boyle's law. So the Boyle's law is again a fundamental gas law which gives the relationship between volume and pressure. So, okay, so here the relationship is established between volume and pressure at constant temperature T. V and P at constant temperature T. So what the law says? It states that the volume of a given mass of any gas, it is inversely proportional to its pressure. Okay, so the volume V is inversely proportional to its pressure P at constant temperature. Okay, the only condition here is that temperature should be constant. So at constant temperature, volume of a gas is inversely proportional to pressure, or pressure is inversely proportional to volume. Either way you state it, the same thing will be there. So volume is inversely proportional to pressure, volume is inversely proportional to 1 by P, or volume is equal to K by P, where K is a proportionality constant. So if we take P to the left hand side, it will go to the numerator and we'll have PV is equal to K. That is the product of pressure and volume at constant temperature. It is always a constant value. Okay, so if we take two such situations, let's say we have situation 1 at constant temperature, okay, at constant temperature, we have two situations. In situation 1, we have pressure P1, volume V1, and in situation 2, we have pressure P2, volume V2. So, the product of pressure and volume in both the cases, it will be the same, equal to the constant parameter. So here, either if you write pressure is inversely proportional to volume or volume is inversely proportional to pressure, both ways it is correct. So if pressure increases, volume decreases. If volume increases, pressure decreases. Inverse relationship. And this is the plot of Boyle's law, where we have pressure and volume in the two axes. Here pressure is taken in the y, volume is taken in the x axis at constant temperature. This is the plot. Okay, so here as you can see, at low values of volume, the pressure value is high, and at high values of volume, the pressure value is low. See, okay, like this. Okay, high pressure, low volume, and here it is high volume, low pressure. Okay, this. So let's say I take this one as P1, this one as V1, and this is P2, this is V2. The thing is that P1 V1 will always be equal to P2 V2. No matter which coordinate you take, it will always be equal as per Boyle's law. Okay, so here we have the pressure of a gas and the volume. So we have this relationship. Volume is inversely proportional to pressure, or pressure is inversely proportional to volume. Product of pressure and volume at constant temperature, that is always constant, equals to the proportionality constant. Okay, and if we try to plot it in a different way, that is, we take pressure as it is and we take the inverse of volume, then we will have a straight line passing through the origin at constant temperature. So this is another way of representing Boyle's law, this way or this way. So this is Boyle's law. Volume is inversely proportional to pressure, pressure is inversely proportional to volume for a gas at constant temperature. Then we have Boyle's law is done. Now we have Charles' law. Okay, so let us discuss Charles' law. So Charles' law, it gives us the relationship between volume and temperature of a gas at constant pressure. Okay, so the relationship, the two important parameters here are volume and temperature, and pressure is kept constant. Previously we had pressure and volume with temperature constant. Here volume and temperature, pressure constant. Okay, so by the way, this was given by Robert Boyle. Okay, Boyle's law, it was given by Robert Boyle. And Charles' law, it is given by, it was discovered by Alexander Charles. So it gives us the relationship between volume and temperature at constant pressure. So what is the statement of Charles' law? Now it states that if the pressure of gas remains constant, then the volume of the gas V increases or decreases by 1 by 273.15 of its volume at 0 degrees Celsius. This is very important. So here this volume is the general volume of a gas at any temperature, and this volume is the volume at 0 degree Celsius. Okay, so if the pressure remains constant, at constant pressure, the volume of a gas it increases or decreases by 1 by 273.15 of its volume at 0 degree Celsius for each 1 degree Celsius rise or fall of temperature. Okay, so for every 1 degree Celsius rise or fall, the volume of the gas, it increases or decreases by 1 by 273 by a factor of 1 by 273.15 of the volume at 0 degrees Celsius. So if we want to express it in a mathematical way, it will be this. So here we have the volume of a gas at T degrees Celsius. Please note that it is in degrees Celsius, and it is specifically, you have to, the equation is different for Celsius and Kelvin. So here this is for Celsius. So this is the volume of the gas at T degrees Celsius, which we'll call V subscript T, this, and V0 is the volume at 0 degrees Celsius, the volume of the gas at 0 degrees Celsius. So the volume of a gas at any temperature specified by degrees Celsius, that is, let's say T, the volume is V0 plus 1 by 273.15 into V0 into T. This is the expression. Okay, let me specify it again by writing it in a different way. Vt is equal to V0, that is the volume at 0 degrees Celsius, plus 1 by 273.15 into V0 into T. Okay, so it increases or decreases by a factor of 1 by 273.15, which is specified here, 1 by 273.15 of the volume at 0 degree Celsius into V0 into T for every 1 degree Celsius rise or fall of temperature. If it is falling, it will become minus. So here it was given for, the rise in temperature. So this is the standard expression. So if we modify it, if we take V0 common, we will have V0 into 1 plus T by 273.15, where T is the temperature in degrees Celsius. Always take care of that. So rearranging the terms, we will have that is equal to V0 into 273.15 plus T by 273.15. Now if you pay attention here, we know that 0 degrees Celsius is 273.15 Kelvin. So when we add 273.15 with the Celsius temperature, we get the temperature in Kelvin. So in terms of Kelvin, we have Vt is equal to V0 into T by T0, where T0 is 0 degrees Celsius, which is equal to 273.15 Kelvin. Okay, this. So we have here, as per this relationship, volume of a gas at any particular temperature T is directly proportional to the temperature T. So V is directly proportional to T. Okay, volume is directly proportional to temperature. That is the essence of Charles' law. Okay, so Charles' law, it can be stated in another way when it is in Kelvin. So whatever, whether it is in Kelvin or degrees Celsius, it does not matter. The essence of Charles' law is that at constant pressure, the volume of a given mass of gas is directly proportional to its absolute temperature. So if temperature increases, volume increases. If temperature decreases, volume decreases. Okay, so if we have a gas container and we measure its temperature, so the volume is directly proportional to temperature. Okay, volume is directly proportional to temperature. So in any case, the ratio of volume and temperature in any particular situation, it will always be the same. Suppose we have two situations. This is in situation 1, we have volume V1 temperature T1, and in situation 2 we have volume 2 temperature T2. Volume V2 temperature T2, the ratio will always be constant because volume is directly proportional to temperature, and the condition is that pressure is constant. Okay, so this is Charles' law. So we have Boyle's law, which states volume is inversely proportional to pressure, pressure is inversely proportional to volume at constant temperature. Then we have Charles' law, which states that volume is directly proportional to temperature at constant pressure. Okay, next we have the third important law, which is Gay-Lussac's law. Okay, and again this is the plot for Charles' law. Okay, simply here we have taken temperature in Kelvin and volume here. Temperature is taken in the x-axis, volume is taken in the y-axis, pressure is constant. So as it is directly proportional relationship, so the plot will be a straight line with a certain slope depending upon the proportionality constant passing through the origin. Okay, so this is the plot of Charles' law. Next we have Gay-Lussac's law. So again, Gay-Lussac's law is concerned with the relationship between pressure and temperature of a gas at constant volume. So volume here is constant, and we have to establish a relationship between pressure and temperature of a gas. So it was discovered by Joseph Gay-Lussac. Okay, so the statement of Gay-Lussac's law is that if the volume is constant, okay, volume is constant, the pressure of a given mass of gas, it increases or decreases again by 1 by 273.15 of its pressure at 0 degrees Celsius for every 1 degree Celsius rise or fall of temperature. Okay, so here it is very similar to Charles' law, but the relationship between parameters is different. Again, 1 by 273.15 factor is involved here. So here we have the pressure at 0 degrees Celsius, which is P0. Okay, so volume is remaining constant. The pressure of a gas increases or decreases by 1 by 273.15 of the pressure at 0 degrees Celsius. Again, P0 is the important parameter for every 1 degree Celsius rise or fall of temperature. So it can be mathematically stated as the pressure of a gas at T degrees Celsius, again it is in degrees Celsius, it is called as P subscript T, the pressure of a gas at T degrees Celsius. It is equal to P0, that is the pressure at 0 degree Celsius, plus 1 by 273.15 of P0 multiplied with T. So it can be rewritten as this: pressure of a gas at T degrees Celsius, that is equal to pressure at 0 degrees Celsius plus 1 by 273.15 into P0 into T. Okay, 1 by 273.15 of the pressure at 0 degrees Celsius for every 1 degree Celsius rise or fall of temperature. So as we are concerned with the rising thing, so that's why the plus sign. If it is falling, then it is negative. So this is the Gay-Lussac's law mathematical expression. So if we rearrange the terms by taking P0, that is the pressure at 0 degrees Celsius common, so we have P0, P subscript 0 into 1 plus T by 273.15. So we have this P0 into 273.15 plus T is equal to 273.15. So we know that 0 degrees Celsius is equal to 273.15 Kelvin. So when we add 273.15 plus T degrees Celsius, we get the temperature in Kelvin. So this is in Kelvin, this temperature. So we can write Pt is equal to P0 into temperature in Kelvin by T0, that is 0 degrees Celsius or 273.15 Kelvin. So T0 is 0 degrees Celsius or 273.15 Kelvin. So here we have a relationship between the pressure at a particular temperature and that temperature. So pressure is directly proportional to temperature. This is the essence of Gay-Lussac's law. So it only depending upon the mathematical equation, whether you are expressing it in degrees Celsius or Kelvin, the equations are just changing here and there, but the essence of Gay-Lussac's law is that pressure is directly proportional to temperature at constant volume. Okay, pressure is directly proportional to temperature at constant volume. So Gay-Lussac's law can be restated as volume remaining constant, that is at constant volume, the pressure of a given mass of gas is directly proportional to its absolute pressure. Absolute temperature. Absolute temperature. Okay, this pressure is directly proportional to temperature at constant volume. Okay, so we have the three important gas laws here. First one, Boyle's law, which states the relationship between volume and pressure at constant temperature. So it is pressure is inversely proportional to volume, volume is inversely proportional to pressure. The product of pressure and volume is always constant. This is the plot, the two ways of plotting it. Then we have Charles' law, which states the relationship between volume and temperature of a gas at constant pressure. So as per Charles' law, at constant pressure, volume is directly proportional to temperature. That is the ratio of volume and temperature, it will always be constant. This is the plot. Then we have Gay-Lussac's law. So Gay-Lussac's law gives the relationship between pressure and temperature of a gas at constant volume. So as per this, at constant volume, pressure is directly proportional to temperature. Okay, so the ratio of pressure and temperature, it will always be constant in different situations, no matter what, because there is a proportional relationship. And this is the plot of Gay-Lussac's law, where we have temperature in Kelvin in the x-axis, pressure in the y-axis. So it is a straight line with a certain slope passing through the origin. Volume is constant. Now, there is another important concept which is associated with these gas laws, which is the ideal gas equation. So here I have written ideal gas equation. So the reason is that gases, they exhibit two kinds of behaviors. One is the hypothetical, explanation of a gas, which is ideal gas. So this hypothetical explanation is for the ideal scenario. We want them to behave in a certain way, but all gases which are which exist in the environment, they are real gases. Okay, so they do not obey the ideal gas law, but this is only for the the formalization of the various behaviors between the pressure, volume and temperature. And the real gases, they follow the ideal gas law under conditions of high temperature and low pressure. But the ideal behavior is studied so that it can be analyzed in a simple and easy way. Okay, so we have the different gas laws. Pressure is inversely proportional to volume, volume is inversely proportional to pressure. Then we have volume is directly proportional to temperature, pressure is directly proportional to temperature. Now if we combine all of them, we will get pressure the product of pressure and volume, it is directly proportional to temperature. Again, PV is a constant, product of pressure and volume is a constant, volume is directly proportional to temperature at constant pressure, pressure is directly proportional to temperature at constant volume, and product of pressure and volume is a constant at constant temperature. So if we combine all of them, we will get PV is equal to RT, where R is a constant of proportionality which is called as universal gas constant. Okay, so you understand this. We have established that PV is a constant, Boyle's law. Okay, PV is a constant, Boyle's law at constant temperature. Then we have Charles' law, which states that volume is directly proportional to temperature. Then we have Gay-Lussac's law, which states that pressure is directly proportional to temperature. So we have these three information. Pressure and volume product is directly proportional to temperature, volume is directly proportional to temperature, pressure is directly proportional to temperature, and product of pressure and volume is a constant. So if we combine all of them, we get PV is directly proportional to T, that is product of pressure and volume is directly proportional to temperature, and R is the universal gas constant. So here the important thing is that this is only for 1 mole of a gas, which is specified by the Avogadro's number. Now if we want to write this equation for n moles of gas, we will have PV is equal to nRT. Okay, PV is equal to nRT, where n is the number of moles of gas. Okay, n is the number of moles of gas, and R is the universal gas constant. So this is the ideal gas equation. PV is equal to nRT. So we have P is the pressure, V is the volume, T is the temperature, N is the number of moles, and R is the universal gas constant. So it has a value, capital R, the universal gas constant, has a value of 8.314. It has other values up to different 4, 5, 6 decimal places. Here I have included up to 3 decimal place. So 8.314 joule per Kelvin per mole. Okay, so here we have established the relationship between various important parameters such as the pressure and volume, then the pressure and temperature, and the volume and temperature of a gas. So we started with Boyle's law, pressure and volume at constant temperature, inverse relationship between them. Then we went to Charles' law, which is volume and temperature of a gas at constant pressure, direct relationship, volume is directly proportional to temperature. And then we went to Gay-Lussac's law, which is relationship between pressure and temperature at constant volume, and that is there is direct relationship, proportional relationship, pressure is directly proportional to temperature at constant volume. Then we combined all of them to get the ideal gas equation, that is PV is equal to RT for 1 mole of gas, or PV is equal to nRT for n moles of gas, with the universal gas constant value equals to this much. Okay, so this is all about the gas laws and ideal gas equation. Okay.